Hello YouTube, this is Eric from Coder Snacks. Today we're going to talk about getting the closest points to the origin from a large file. Let's get started. Working with large files takes away some of our tools, but also gives us a few interesting strategies such as reservoirs and streaming algorithms. Let's dig in. First, we should ask some questions. How big do we expect X to be? Notably, does it fit in memory? How big do we expect the data to be? How is the data stored on disk? What is the format of the points? What is their range? For our question, we'll assume that X easily fits in memory, say less than 1,000 elements, and is far smaller than N. We'll assume the data is large enough to not fit in memory, and the points are doubles, stored as text. Note, this is inefficient. A double is 8 bytes, whereas this representation takes about 20, but for illustrative purposes, it's fine. It is worth thinking about how to store it more efficiently, however. For testing and illustration purposes, we have a dataset of 1 million points. This dataset fits in memory, but can run in a few seconds instead of a billion points, which takes far longer. We promise not to load everything into memory. First, let's get an idea of how long reading the points and converting them to numbers takes, as a baseline. Here's a simple loop that reads each line and converts the line to 2 floats. We'll use the timeit module to see how long it's taking, and we'll see it's a little over a second. We're more interested in the min here than the average. This is running on a computer where other things might be happening, such as, recording video, which can add some noise to the timing. We want to ensure, since we're never using these XY values, that the interpreter isn't optimizing the loop away. Let's add a simple addition in to use these values. It takes slightly longer. It's likely not optimizing, so we'll revert. What algorithms would we use if the data were smaller? We could load the data into memory and use selection rank to find the kth smallest distance. This would take O of n time, where n is the number of elements. Unfortunately, we're assuming the file is too large to load into memory. We could take a similar approach by repeatedly reading in the file, but reading the file in takes a lion's share of the time. This would be inefficient. Let's begin with a brute force approach. We said that k fits in memory. What if we keep the best k we've seen in memory using insertion sort? When we see a new element, we'll insert it into our list and then remove the largest distance. Here's some code. We read in the file point by point. For each point, we insert it into our sorted best list, and if we can't, we append it to the end. Then we trim the list to our best k. At the end, we return the best. When we run it, we see it's taking about 2 seconds over our baseline. Each time, we run all the tests, so if something is going on with the processor, it affects all the tests, and we're not running some tests in drastically different conditions. This is still very rough. If we really wanted to do timing tests on this, we'd want to do way more trials, but this should be good enough for our purposes. The runtime complexity of this code is O of n times k. For each element, we do O of k work inserting it. Let's try to improve this. One idea is to sort the k list after every element. This is O of n k log k theoretically, since we're sorting k elements. O of n k log k is worse than O of n k, right? Let's code it and find out. We append each point to our best list, and then sort and trim the list to the smallest k elements. When you sort a tuple, it uses the first element as the first sort key, which is great for us. At the end, we return the best k points with distances. Is O of n k log k worse? Apparently not. This is probably because timsort, the sort Python uses, is great for nearly sorted lists, effectively O of n. Our list is always nearly sorted. But sorting the list for every element is a lot of work. Could we sort it less often? Let's sort and trim when we reach 4 times k elements, and we'll make a new function to do this. 4 times k gets us a pretty fair speed up, but increasing it to 10 times k doesn't help. At some point, the list is poorly sorted enough that the sort is closer to k log k than O of k. We could tweak this more, but let's move on to a more optimal solution, using a heap. Our current algorithms are at least O of nk because we're doing something O of k for every element. We'd prefer to do less work, and here's where a heap comes in. Think of a heap as a complete balanced binary tree. If you want to hear more about trees, check out this episode. There are 2 kinds of heaps, max heaps and min heaps. In a max heap, a parent's value is greater than either of its children. In a min heap, a parent's value is less than either of its children. We call this the heap property. For illustration, we'll use a max heap. Note that this is not a binary search tree. Finding an arbitrary node in this tree requires searching the whole tree. We can't easily say if a value is on the left or the right of a node we're given, only if it's not below. When we add an element to a heap, we add it at the leftmost leap on the bottommost unfilled level. Then, we check to see if this violates the heap property by comparing it to its parent. If it does, we swap the parent and the new node, and then check the new parent. We repeat this until the parent is greater than the new node, or the new node is the root. This takes O of log n time. There are log n levels in a balanced binary tree. When we remove, or pop, the top element from the heap, maintaining the heap property is more complicated. First, we swap the root with the last leaf in the heap, which we can then remove to return at the end. Now we have to fix the tree. We do this by percolating down the node which we swapped into the root position. We look at the left and right children, find which one is greater, and swap it with our root node. We have to swap with the greater node or we'll violate the property. If we swap the lesser node, it would be less than one of its children. Then, we repeat the process, looking at both children, swapping with the greater, until our node is greater than both children. We've restored the heap property. This also takes O of log n time. If we want to see the maximum element, that's O of 1. We look at the root. We could implement this with a tree, but normally we implement heaps with arrays. To visualize this, let's change all the nodes to indices. We make the root index 1, its children 2 and 3, and so on. A useful pattern emerges. Each node's child are in nodes n times 2 and n times 2 plus 1. This lets us take advantage of a simpler data structure stored more efficiently in memory while keeping the advantages of the tree, log n insert and remove. Heaps are commonly used for priority queues. You can imagine having a bunch of objects representing things to do with some priority and then popping the items from the queue in priority order. We used a priority queue in our Finding the Shortest Path video. Back to our problem, we can maintain a max heap of the best k elements we've seen. It's a little counterintuitive to use a max heap when we want the minimum distance, but at each step we want to see if our new point's distance is less than the best k nodes we've seen so far. If our point's distance is less than the maximum point in the heap, we want to keep it, and we'll add it to the heap. Therefore we use a max heap. We're comparing a new point with the maximum of our k minimum elements. Heaps can be tricky to implement in practice. We will instead use the built-in heap queue. Unfortunately, heap queue is a min heap, not a max heap. To get around this, we'll negate all of our distances, making the 20 closest to 0 minimums instead of maximums. Let's write the code to do this. We read in the file the same way as before, with the additional step of negating the distance so we can use the min heap as a max heap. Until we have k elements, we always push the item onto the heap. Once we have k elements, we push our new item and pop the top item, which is the maximum, off the heap, leaving us with a heap with the best k elements. At the end, we negate the distances again, making them positive, sort them, since the heap is not in sorted order, and return the elements. When we run it, we see that it's the fastest solution thus far, and asymptotically, it's the fastest solution running in O of n log k, n items, log k effort per element. We can make this solution even faster by getting rid of this square root. We don't need to know the precise distance, as long as we can know comparatively which distances are better or worse. For our purposes, the square of the distance is as good as the distance. In an interview, this would be an excellent solution, and this is normally where I would roll the challenges out. The problem is, asymptotic complexity doesn't always lead to fastest runtimes. Don't prematurely optimize. Let's go back to our original brute force O of nk solution. If I add a check to see if my item is less than the largest item in the list and make the square root change, it's now faster than the heap solution. Adding the same check to the heap solution improves it, but doesn't make it faster than the insertion solution. Additionally, all of these methods would shift in effectiveness as we change the sizes of n and k. The larger n is, the less items go into your top k, but the larger your k is, the more often they do. Here, for example, is the same code, but with k equals 200. The best heap version doesn't get any slower, but now the insertion method is a few percent worse. I like this interview question as a way of discussing a variety of techniques, but it's difficult on a whiteboard because the things that make programs fast in practice aren't always obvious from the whiteboard. If you're trying to solve this problem, it's vital to do testing for your actual use case if you want to wring out the last bits of speed. Big O runtime complexity does not always indicate the best solution. And now I will roll out the challenges. Start by implementing your own heap class, then use it in this problem and see how much slower, or faster, it is. Next, you might imagine that if you have a bunch of items and want to form a heap for all of them, it would take n log n time since you have to add each item individually. But you can form a heap from a list of elements in O of n. How? This approach is good for large files, but if you have truly large files, say terabytes or petabytes, you'll want to make improvements. How could you do this on multiple computers, or using multiple disks? Finally, implement this in another language, like Java, C, Go, etc. An unpolished Java solution using a priority queue runs 40 or 50% faster than this, meaning the problem is solved faster than you can read the data in Python. Next time, we're going to talk about binary search trees. Write a function that, given a pointer to the root of a tree, determines if it's a binary search tree or not. I hope you got something out of this video. If you have any questions, comments, something I've missed, or problems you want answered or covered, let me know in the comments section below. And if you enjoyed this video and want to see more, it would be great if you liked the video, subscribed, or both. I really appreciate it. See you here next time on Coder Snacks.